Jan is the embedded engineer and machine learning advocate from HMPulse. He's the CTO. I mean, one interesting thing that I found that there is, his name is on a monument in San Francisco for some reasons. So probably you will tell us about this and forget about the rest.
Thank you. All right. Can I get the clicker? Yeah,
Shall I
so
take that? Yeah.
I think when Mozilla was 15 years old, the open source organization that builds Firefox, among many other things. Can I have a clicker? They put a monument up in downtown San Francisco in front of their office with all the contributors that have committed code to Firefox and all the other projects. And it's still there 10 years later. I don't have a clicker. Oh, there we go. So that's how I got my name on the monument. So hi, I'm Jan Jungbaum. I really like to be part of this track and not part of the research or whatnot track, not because I don't like research, but because I want to talk about how people are really using TinyML in real devices. So I have a couple of use cases, a couple of customers that we've worked with to make that happen in the next 20 minutes. All right, so I assume everyone knows this, but HMPulse is a platform to build machine learning for really small devices. I don't really like TinyML anymore. I realized that 6, 7 years ago when we all started working on that, that was sort of the end goal. I like embedded machine learning better. Not everything that we do is actually tiny. Not all the models that we actually build go into really tiny devices. Sometimes we do hybrid deployments. So rather think about machine learning embedded in devices. So that we're trying to build. Look at the spike of projects, right? So this is a hockey stick, and that's only the graph up until last year. That's the number of projects that people have created on HMPulse. So real ML workloads that they've built. And that already looks cool. And this is actually what happened in the last 12 months. It's insane. We just hit over 200,000 projects on HMPulse, which is insane, right? Like 7 years ago when I was at ARM together with my co-founder Zach, we thought about this idea like, we think there is something where people want to build their own machine learning models and run them on small devices. And now every day there's about 500 new projects being created. And that's 2 times as much people as here in the room, right? There's really a movement that we all started together. People are really interested in building these types of things. And it's not just research, it's actually taking that, putting it into practice and actually building real models that they can go ship. So that's really important. That's just a community tier. What I'm even more proud of is actually the large number of enterprises that trust us, right? So I'll talk a little bit about Aura. I'll talk a little bit about Poly in this talk. I'll talk a little bit about No Labs. These are all customers who have gone through production, right? 4 years ago, I think it was the first time that I was at a TinyML Summit in California, I don't think we had any customers in production, right? As the complete industry together. Everyone was talking about new accelerators, new models, whatnot. Now we have customers doing, with two of these logos actually have shipped more than 1 million devices. We have people actually shipping real models, real TinyML models, putting real intelligence into these devices. Much more interesting. The 200,000 projects are cool, but this is way, way cooler. Yeah, that's again, it's also cool. All right, so let's take a small step back to 2019. Which is the year that I founded HMPulse, co-founded HMPulse. And our very first customer was this little, well, not very little anymore at that point, Finnish-American company called Aura, and they make a sleep ring. So Aura approached us with the idea like, hey, we think there's something in using data to build the next generation of algorithms. Can you guys help? And we were like, okay, sure, we just founded the company 2 months ago. We don't have a product yet, but of course we can help. Like, how hard can it be? So all of a sudden, I found myself in a sleep lab in Singapore. This was in November 2019. In a sleep lab in Singapore with 40 Aura rings and a guy completely hooked up to multiple machines. So what they wanted to do, so Aura is doing sleep quality monitoring. At least that was the initial idea. So they have a ring, and that predicts your sleep stages throughout the night, and based on that, they'll give recommendations of how well you slept, if you need to take it slow, etc. And their original algorithm was built by hand by a couple of guys in Finland back in 2015. So there's two questions actually that I wanted to understand. First, how well is our current generation algorithm working? Like, we think it works well, we get good feedback from customers, but how good is our sleep staging prediction actually? And then second, can we actually take a more data-driven approach to build a next generation algorithm? And then, build based upon kind of the foundation that you build, right? Now you have a proper clinical validation cycle that you want to set up. Can we actually do more than just sleep stages? So for me, this was a crash course in sleep stage prediction. So how do you go build a data set that can do that, right? Sleep, it sounds very fuzzy, and it's not even an exact science, which is the interesting bit. So first of all, we need to get good high quality data, reference data. So they hook this person up, ECG, EEG pods, they hook them up to a machine. This takes about half an hour to set up per night. So that's really annoying, and it actually needs to be done by a trained sleep technician. So this was at the University of Duke NUS in Singapore. So they actually had PhDs that were trained in hooking people up to these machines. So then you get about 30 channels of data at 256 Hertz. That we store in an EDF file, so that's what you see here on the left. Then, that's the second stage. This is actually where the interesting bit is. Then a trained sleep classifier, a person, looks at that ECG, EEG diagram, and then says, hey, actually this was light sleep, this was REM sleep, this was deep sleep, and this was awake. It's very interesting. So already, because there's a human in the loop, you can understand that there's never 100% accuracy in this model. You can never do that. If two trained sleep stage technicians look at the same EDF file, right, on a 5-stage classifier, there's about 82-83% agreement between them. That's how fuzzy it is, and that's kind of the best you can do, which is an interesting bit, right? We're always talking about, well, like, I have like 0.1% extra here, and maybe I can read like 92% on that thing, and now we actually have a real use case where 83% is the best you can do. Sort of funny. So then we also need to get data from the customer's device. So in this case, this person wears 3 Oura rings, 2 commercial and 1 research version that could, or 2 research versions that actually could store the raw data, and then the commercial version because we wanted to understand how well the current algorithm was doing. So we feed that data into a Gympulse. And then we use the gold standard labels, so what the sleep technician actually thought were the labels, we use that to label our data. So now we combine these really high quality labels, right, with the sensor data we got from Ring, and that's only 3 sensors, PPG, temperature, and accelerometer. And through that we train a new model. Actually pretty easy, right? I mean, once you have the labels, all of this stuff becomes trivial. Getting the labels here is really expensive. So it costs about $1,000 to do 1 night of sleep in a sleep lab. And for the new model, the one they published, the first version, they I think 1,200 nights of sleep that went to the algorithm. So that's just 1.2 million just in the cost for the sleep lab, which is pretty insane. But I do think this is a really nice fit for TinyML, right? So a good data set is not just data, it's data plus labels. And if you have a reference device, in this case, your ECG diagram, that can give you high quality labels, that means that 50% of your work is done already. And it also means that you can scale this up really, if you set this up correctly, you can also scale this up very quickly, right? Once you have your complete clinical pipeline running, you can go to another sleep lab and say, hey, here's the complete protocol, put these rings on, put these ECG dials on someone's head, and now we have more data. That's really powerful because do you want to go spend over $1 million to collect data if you don't know whether this works, yes or no? No, probably not. You want to do this on 100 nights first, see if that works, and then scale it up really, really quickly. And this is actually a really common pattern that we see in health. For us, the interesting bit, right, when we started at Gympulse, I really thought like predictive maintenance, that's going to be the big money maker. Well, we realized no one wants to pay for something that might break in 10 years. Customers in health, though, are willing to actually open up their wallets and go pay because they need to drive innovation. There's a lot of money to be made in health. For example, Dexcom, which is the largest manufacturing of devices to measure glucose, is a $48 billion company. right? That's just one company doing one use case, $48 billion in market cap, insane. So first, health, really important, and then stuff actually production line monitoring and stuff that can happen right away and can break at that very moment, not stuff that breaks 10 years from now. So in health, we see this a lot, right? So you have a reference device that can already get the right readings, so polysomnography in sleep, a chest strap if you want to do heart rate, or, and this is why I alluded to the glucose monitoring, there's another customer of ours, Know Labs, they want to build a non-invasive glucose monitoring device. And the interesting bit, so you already have a reference device. So that can be a finger stick, but Know Labs is also using Dexcom devices. So already devices in the field that are seen as kind of gold standard by the market, use them as your reference devices. Really interesting. And then you want to use machine learning to either make this smaller, cheaper, more power efficient, etc. Right? The interesting bit is that we see that a little bit outside health as well. So we can use big models. That's even better, right? Because in this, if we use a really big machine learning model, there's not even a human in the loop anymore. It's even better. So, for example, I don't know if you guys saw the demo we did around on microcontrollers with FOMO. What we did there first, so I wanted to do something where we labeled beer bottles and recognize them. So it took YOLO V5, really big model, doesn't run on MCU. But I used that to go label my complete data set because YOLO V5 understands what a bottle is. So you just feed 1,000 pictures of beer bottles in. I let YOLO V5 label that and then I retrain the model. Really awesome. And also then it goes really fast, right? You just snap a bunch of photos. I don't need to care about labeling or drawing bounding boxes or whatnot around it. All of a sudden I have a really high quality labeled data set and I just need to retrain. Another one recently came out, the Whisper model, which actually is speech to text. It's been tremendously helpful in building high quality keyword spotting data sets. So I can just feed a bit of data in, and it's actually from a talk I did last week at Particles Spectra conference. I speak English with a pretty heavy Dutch accent, and Whisper understands this perfectly. And there's a version of Whisper, Timestamp Whisper, which actually gives me exact timestamps of all the words. So the really interesting bit here is that we can just feed 1,000 hours of radio through Whisper and actually have a really high quality annotated data set that we can then mix and match. So even in that I can find Tiny and I can find ML, there's probably a whole bunch of people that have said that, mix them together, create artificial data and actually create a training set of data without actually having to go and collect that with people. So we did this with HP Poly the old way. So they made headsets, and they wanted to add voice commands. They actually needed to source with a third-party company a really big data set. They had 11 keywords, I think, on there, times 8,000 samples, I think, per keyword. That's a lot of money that you need to spend. This is something that I think is going to be disrupted completely with Whisper. Another one is that we can use big models to help label is with Segment Anything, new foundational model from Meta. So the interesting bit, this is actually a data set from Advantech, on production line monitoring. And what we're interested in is the trays and the hands, the position of the trays and the position of the hands. So you see tray, and tray here, and there as well, and you see the hands here. Very tedious to label this, incredibly tedious to label this. The interesting bit of Segment Anything is that it can create segmentation maps. It doesn't know of what, but it can create segmentation maps from this data without user input. It's really expensive, like it takes on an NVIDIA A100 GPU, it takes 3 seconds per image. But that's a lot cheaper than having someone label by hand. So this is the output that you actually get. So we create clusters of all the segments that we find. So here we actually find a cluster full of trays. And it means that I only need to label that cluster. So not completely human out of the loop, but a lot easier than having to do this by hand. And this is actually what we end up with, a really nicely, almost automatically annotated data set. Really cool. All right, so let's go into detail a little bit more on like how we approach this with a customer. So back in 2022, another wearable maker, not Aura, actually came to us and they said, well, currently we license a cloud-based algorithm. So we license silicon plus the algorithm from a large manufacturer of, I can't name the company. No. Well, let's say a large electronics manufacturer based in Eindhoven. And they think that works relatively well. The problem is that because this runs in the cloud, they can only run it at the end of the night. So at the end of the night, they upload all their features, they get sleep state prediction back. Not entirely sure how well that works because they don't have access to the actual data, they don't have access to the actual algorithm, but relatively okay feedback from customers. And now they wanted to do something new. They actually say, hey, we want to run this on device, not because we're unhappy with the predictions or whatnot, but we want to do something that requires us to have this data while someone is still sleeping. We want to wake this person up while they're in light sleep. So you set your alarm. So let's say we put our alarm here, right? And then we take about half an hour before the alarm. And then when we see like a minute and a half of light sleep on your PSG sleep score here, and at that point we'll wake you up. And the idea is then you wake someone up while they're not in REM sleep or deep sleep, so they wake up more or less fatigued and all this kind of stuff. So for this, we can't use the algorithm that they're currently using because probably it's too big, and second, we don't even have we probably can't get access to it. So let's go reverse engineer that. Oh yeah, so here we wake up. That's actually the moment that we've been in light sleep for a little bit. So for this, like the biggest thing is like, how can we make sure that we automate this? The really interesting bit is we have the labels, right? Because at the end of the night, we send all the features to their current provider, and they give us back a really nice, annotated night of sleep. And we already have the data because we sent that to the cloud provider. So the brilliant part is that we can completely automate that. So the first thing is just, let's fetch all the data from the device. So we intercepted the data that they currently sent to their current provider, just drop them in S3, and then feed that into Edge Impulse on a daily basis. Labels plus the data. Second, we set up a pipeline. In all fairness, like people think of Edge Impulse as a machine learning company. We're a pipeline company. We run hundreds of thousands of hours of compute every month for our customers just in creating those data sets. Really interesting. So we fetch data from multiple sources, right? So the internal data lake that they have, the cloud labeled data we get from the provider, and then some external reference devices too, right? So we'll have someone sleep with a Fitbit on as well, just so we can see like, hey, how well does the data from Fitbit align with the data they get from the current provider? Then we verify the data is correct and complete. Are all channels available? Is there no truncated data? Then we find sleep sessions in here. So we get all of their data in. So we're looking at, hey, we're actually only interested in nights of sleep. So that's stuff that spans 2 days typically. So we need to combine that. We fetch metadata, and then we run that daily or on demand. So a really interesting bit, what I've learned is that checklists are probably one of the most powerful features in our tool. Skip all the machine learning stuff. Just very simple, like, is this file there? Is that file there? Is that file there? And the biggest trick that I've learned from a customer, from Raphael at Aura, brilliant guy. He said, hey, actually, if you want to know if you're looking at the same, if you get data from 2 sources, right? You get data from your internal source and you get data from a reference device. Are you looking at the same night of sleep? How do you know that? Because the sleep lab makes mistakes too. And once you have mislabeled data in your data set, it's really hard to kind of get rid of that and to detect that. So the trick that we've learned is use correlation. So take something that should be correlated, right? So the heart rate based on the ECG data and the heart rate you get from your ring, for example. Just overlap them. Is there correlation, like we see here? Awesome, that's good. There's no correlation, probably something is wrong. You can also fix timed synchronization here, right? You have devices that have drift or whatnot, and if you're off by half a minute by the end of the night, that means that you're going to have terrible accuracy. So this way we can also shift time. Look at time. And then last, now that we have a really high quality data set and something that gets better every day because we set all these pipelines, every time someone sleeps with the wearable of our customer on, a day later we have the data labeled and with a little check mark that everything is okay next to it, and we can feed it into the ML algorithm. So the initial exploration, fine, do it in SageMaker, do it in a notebook, go build out the features that you need, the machine learning model. But after that, I'd love to host that pipeline for you because now you can retrain on a daily basis. And then we draw really nice little graphs for your manager, showing that your data set quality goes up over time. And hopefully your accuracy actually goes up over time. So that's kind of everything there is to it, right? Get your data flowing, then retrain on a daily basis. And then if all of a sudden we see like a drop in accuracy or something, that's a good indication that something weird is going on. Let's actually go do that. And last, let's get that to run on device. So typical feature set of a wearable that does sleep, has PPG data, temperature, and accelerometer. So there's multiple PPG sensors. We first do the feature extraction. Then we use a machine learning, a classifier. Might be a neural network, might actually not be. New customers actually using XGBoost, not even a neural network. Fine by me. The interesting bit that we then learn is actually that 90% of the work and 90% of the compute is not in the machine learning algorithm. It's all in the pre-processing. It's cleaning up the data from a PPG sensor, removing artifacts. A PPG sensor is incredibly noisy. So one of the tricks we've learned is like, hey, actually, if we use the accelerometer as well, we can sort of see when the movement is happening, and then we can do artifact removal by using the accelerometer as a secondary device. I don't need any machine learning for that. It's just good old signal processing code. So the problem with all of that is that the feature extraction is such a fundamental part of your machine learning pipeline, but it's not a neural network, so you can't just throw it through a neural network compiler and run that on device. So this requires, lots of back and forth between the domain expert that writes that feature extraction pipeline and your embedded team that needs to implement that on device. And what we had with this customer is that they actually had a window of data of 30 minutes. And they can't store 30 minutes of raw PPG data on a small wearable. So we say, hey, actually, now we need to go back. So actually, can you use a window of 4.5 minutes? Okay, shit, now I need to do my complete feature extraction completely again. And oh shit, now I've had 3% accuracy drop in my device. So now we need to go back and forth, like, is it actually worth it? Really annoying. Because there's no regard for this computational expensiveness, which is relatively easy with a neural network, right? You can just take whatever you've trained and throw it through a compiler, and we'll probably tell you how big it is. So, this really cool thing, I'm closing in a minute. We've been working on something really cool, and we just won our first customer. It's actually Fortune 170 or something, what Zach always says. It's like, hey, actually, can we take this feature extraction and also show that as a compute graph? So not just a neural network as a compute graph, but actually have your feature extraction as a compute graph. So we're building on top of what we have already with the Ion compiler and with and then combine it with JAX. Come talk to me if you find this interesting. But essentially what this gives you is that our customer writes stuff in Python, just normal Python, bit of vector math in there. We run it through our compiler toolchain the same way as we do it with neural networks and outcomes, very efficient C++ source code. So now we have this whole pipeline, feature extraction, neural networks, whatnot, in one go. Customer writes it, gets immediate feedback whether it's going to work on device, and then we can run it there. So, I'll use 30 more seconds here, sorry. So my recap here, it all starts with labels. Labels are probably even more important than data. Data is relatively easy to get, right? I mean, you just stick a device into something. Getting the labels, that's what it's all about. If you have a big model somewhere, use that, leverage that to dramatically cut down the time and cost of building that model. And if you already have a big model, well, then you probably are already 80% there in actually going to build something for TinyML. So with that, I'm sorry for going over time, but see you the next 2 days.
Thank you, Dan. I think we have